What we are going to do in this tutorial is to find the Laplace transform of a polynomial to the nth power t to the power n multiplied by a function f of t. What we have been doing in the previous videos is finding the Laplace transform of a function f of t, but we will have to now multiply the function by a certain polynomial and we take the Laplace transform of that. So what would be the Laplace transform of this particular function? So let me write it here. Why not? So the Laplace transform of a function f of t, this is equal to the integral from 0 to infinity of e to the negative st multiplied by the function f of t and then dt. So this one, we are told that this one is capital F of s, and this is equal to the integral from 0 to infinity of e to the negative st multiplied by the function f of t and then dt. Cool. Now this is what we have. How do we now find the Laplace transform of a polynomial multiplied by this function? So how do we get t to multiply here? The only way we can have t multiplying this function is when we take the partial derivative of this exponential function with respect to s. When we differentiate this one with respect to s, we are able to bring the t down to multiply the function, which conforms with what we want to find here, right? So the trick that comes to mind is to differentiate this one here with respect to the constant, with respect to the variable s. Right, so now let's do that and see what happens. So we are going to find the nth power of t multiplied by f of t. So to bring t down to multiply this, we will have to differentiate this one with respect to s. So let's do that, but we want it we want to have t raised to the power n. So what I have to do is to differentiate it like n different times. So I'm going to differentiate this one n different times. So ds raised to the power n like this. That is differentiating the Laplace transform of f of t n different times, and this is equal to the integral from 0 to infinity and taking the partial derivative, that's the nth power of this function e to the negative st multiplied by the function f of t like this, and then dt. Cool. So the left hand side remains as this. So that is what we have over dsn, and this is equal to what? So now we are going to differentiate this one with respect to the Laplace variable s. So this one is a constant because it has no s. So this is a constant, and now we will have to differentiate this one with respect to s. So when we do that, we have to differentiate the power, which is negative st. When we do that, we are going to get negative t. So this negative t is going to multiply the function again. So negative t e raised to the power negative st and then f of t and then dt. But this is just differentiating this function only one time. So, but we have the nth derivative, the partial derivative of this function with respect to s n different times. So when we do it one time, this is what we get. When we do it for the second time, we are going to get something like this. That is all this one raised to the power 2. When we do it for the third time, this is going to raise to the power 3. When we do it for the fourth time, this is going to be to the power 4, and so on and so forth. So doing it for n different times, that means that we are going to have negative t raised to the power n, and this will be the nth derivative of this function with respect to the Laplace variable s. So let me clean this one here, make it a bit cleaner. Alright, cool. So now let's apply some laws of indices inside here. So this one is equal to the integral from 0 to infinity of, this can be written as negative 1 raised to the power n t raised to the power n, and then e raised to the power negative st times f of t dt. Now you see that we have gotten t raised to the power n, which we can multiply with our function. That is what we are seeking to find, the Laplace transform of that particular function. Alright, cool. So now the left hand side is the derivative of the Laplace transform of the function f of t with respect to the Laplace variable s. This one is a constant in the t world. I'm going to pull it out of the integral. Then I'm going to have the integral from 0 to infinity of e to the negative st. And this is multiplied by t to the power n and then f of t dt. Recall, the definition of the Laplace transform of a function f of t is the integral from 0 to infinity of e to the negative st multiplied by the function we are seeking to transform. So the Laplace transform of this one that we want to find is equal to the integral from 0 to infinity of e to the negative st multiplied by the function, that is this function. So this one is a Laplace transform of this particular function. So let's write it there. So we are going to have this divided by dsn to the power n, and now this one is going to be negative 1 raised to the power n, right? And now this one is what we call the Laplace transform of t to the nth power multiplied by the function f of t, like this. We want to isolate this one, so what I have to do is to divide both sides by negative 1 raised to the power n. I'm going to do the same thing here to maintain equality. When I do that, this one is going to cancel with this, and now what is left is the Laplace transform of the function that we want, t to the n multiplied by f of t, and this is equal to what? So this is equal to 1 over negative 1 raised to the power n. This is multiplied by the nth derivative with respect to s of the Laplace transform of f of t. Cool. Now this is equal to what? This one can be written as this. 1 can be written as 1 raised to the power n all over negative 1 raised to the power n, and multiplied by the nth derivative of this dsn. Cool stuff. So the Laplace transform of t to the nth power multiplied by the function f of t, this is equal to, applying the laws of indices, that is going to be 1 over negative 1 all this 1 raised to the power n, and this is multiplied by the nth derivative of this over dsn, and this is equal to what? 1 over negative 1 is negative 1 raised to the power n multiplied by the nth derivative of the Laplace transform of f of t. Cool. So that means that the Laplace transform of the function t to the n multiplied by f of t is just taking the Laplace, taking the derivative, the nth derivative of the Laplace transform of the function f of t. So all over dsn, like this. Cool stuff. So we have established the result, and now let's fill our table. So the table here, we are going to write negative 1 raised to the power n, and this is multiplied by the nth derivative of the Laplace transform of f of t, dsn. Alright, so now I can't conclude this video without using this to work examples for you to see. So now the next task for me is to use this one to work few examples, so we see how it is applied. Okay, cool. So now let's solve two examples. So the first one, let's find the Laplace transform of something like this, t multiplied by the cosine of t, like this. So here what we have to find is the function n. We have to find what n here is, and we have to find the Laplace transform of the function f of t. So here n here is equal to 1. So n here is equal to 1, because here t is raised to the power 1, which is equal to n that we have here. And now f of t here is equal to our cosine function, which is the cosine of t, that is f of t. So now if f of t is equal to the cosine of t, we can find capital F of s, that is the Laplace transform of the function cosine of t. So if the function is cosine of t, then its Laplace transform is going to be, we have done this before, we have s divided by s squared plus 1 squared, which is 1. So s over s squared plus 1 is the Laplace transform of the function cosine of t. Now that we have all this, we can find the Laplace transform of this. So the Laplace transform of t multiplied by cosine of t, this is equal to, so we have negative 1. We are now going to use the formula that we found, negative 1 raised to the power n. N here is 1, and now we are going to differentiate 1 all over ds1 of the function f of s, and f of s is that, and that is going to be s divided by s squared plus 1, like this. Cool. So negative 1 raised to the power 1 is negative 1. and this one is just like the first derivative, so that is the same as negative the derivative of this function s over s squared plus 1, like this. Cool. So the Laplace transform of t multiplied by the cosine of t, this is equal to what? So negative outside. Now let's apply the quotient rule. So the quotient rule, what we do is to take the square of the denominator, which is s squared plus 1. So we have to square this, right? And now the numerator, we have to keep s squared plus 1 constant, and then we differentiate s, which is 1, minus we keep s constant and we differentiate s squared plus 1, which is 2s. So this is equal to negative into, now let's expand, that is going to be s squared plus 1 minus 2 s squared. This is divided by s squared plus 1, all this one squared. Cool. So the Laplace transform of t multiplied by cosine of t, this is equal to negative into, now the numerator is going to simplify to 1 minus s squared. This is divided by s squared plus 1, all this one squared. But this negative is going to reverse the numerator, that is going to be positive s squared minus 1 all over s squared plus 1 all squared. Cool. So that means that the Laplace transform of t multiplied by the cosine of t, using our formula that we derived, we are going to end up with s squared minus 1 all over s squared plus 1 all squared. So cool, right? And now let me do another one for you to see. So we are going to work another one. Let me do this one in the white pen. So we are going to find the Laplace transform of, let's say, t squared, but here we have function here is going to be sine of t, like this. Okay, so now we are going to find n, what n here is, and now capital F of s. Cool. So here n here is equal to 2, that is the power of this polynomial 2. We have the function here f of t, the function here is the sine of t, right? That's the function sine of t. So if f of t is the sine of t, what is the Laplace transform of that function sine of t? The Laplace transform is normally a all over s squared plus a squared. A here is 1 divided by s squared plus 1 squared, which is 1. So 1 over s squared plus 1 is the Laplace transform of the function sine of t. Now that we have that, we can find the Laplace transform of t to the second power times the sine of t, like this, and we are going to use the formula. The formula is that negative 1 raised to the power n multiplied by the nth derivative of the Laplace transform of sine of t. So negative 1 raised to the power n, n here is 2, that's what we have, and then we are going to have the nth derivative d square dS squared of the Laplace transform of the function sine of t of f of s. F of s here is this guy, and that is going to be 1 all over s squared plus 1, like this. Negative 1 squared is positive 1, so in the end we are differentiating this one 2 times. So we are just differentiating this guy 2 times. So this is what we have for the Laplace transform of t squared multiplied by sine of t. So now let's solve this. So this one is going to be d ds, and then we are going to differentiate this one again. So we are going to have this, so d ds like this of 1 all over s squared plus 1, like this. So we are differentiating it 2 different times. So that's what we have. And now the Laplace transform of t squared multiplied by sine of t, this is equal to d ds, right? Now differentiating this one, let's do that with respect to s. We are going to use a quotient rule. So when we differentiated for the first time, this is what we had, right? So let's do that. So this one is going to be s squared plus 1 all squared at the denominator, right? And now we are going to keep s squared plus 1 constant, and then we differentiate 1, which is 0, minus, keeping one constant, and we differentiate s squared plus 1, which is 2s, like this. Cool. So this is equal to d ds. We are going to differentiate again, but the numerator is just simplifying to negative 2s, like this, and this one is divided by s squared plus 1 all squared. Cool. And this one is the Laplace transform of t squared multiplied by sine of t. The Laplace transform of t squared multiplied by sine of t is equal to, let's differentiate again. This negative 2 is a constant. I'm going to bring it out, and then we are going to differentiate this. So differentiating this one is going to be s now multiplied by s squared plus 1 raised to the power negative 2. That is, this guy becomes negative 2 on top. And now what do we have? We can apply the product rule here instead of a quotient rule now. Negative 2 all the way in front. Product rule, I am going to keep s squared plus 1 raised to the power negative 2 constant and differentiate this, which is 1, plus I am going to keep s constant and differentiate this one. And differentiating that is going to be negative 2, then s squared plus 1 raised to the power negative 3, and chain rule, differentiating this one, that is going to be 2s, like this. So this one is the Laplace transform of t squared multiplied by sine of t. So the Laplace transform of t squared multiplied by sine of t, this is equal to negative 2. Now let's simplify what is inside the bracket. This one is 1 over s squared plus 1 all squared. Cool. And now here we are going to have 2 times 2, which is 4, and then s times s, which is s squared. So we are going to have negative 4s squared, like this, negative 4 s squared. And this one is divided by s squared plus 1, all this one raised to the power 3. Cool. So now the LCM here is going to be s squared plus 1, all raised to the power 3. Now this divided by this is s squared plus 1. And now we have minus this divided by this is 1, and 1 times the top is going to be 4s squared. All this one is multiplied by negative 2 in front. This is the Laplace transform of t squared multiplied by sine of t. So Laplace transform of t squared multiplied by sine of t is equal to, so here negative 2 into, so now the numerator becomes 1 minus 3s squared all over s squared plus 1 all raised to the power 3. And now multiplying by negative 2, what do we get? Multiplying by negative 2, we are going to have, let's say we have 2 outside here. Multiplying by just negative, we have 2 outside. Then we are going to have 3s squared, and now minus 1, like this. We are just multiplying by negative 1 instead of all the negative 2 divided by s squared plus 1, all this one raised to the power 3. So finally, the Laplace transform of t squared multiplied by the sine of t, this is equal to 2 times 3s squared minus 1 all over s squared plus 1, all this one raised to the power 3. Cool. And this is how you use the formula to find the Laplace transform of a polynomial multiplied by a certain function f of t. So this is how I solved it. If you find this video helpful, please give me a thumbs up and subscribe to Calculus Diaries. And then in my next video, I will use these formulas to find the Laplace transforms of various functions. So subscribe to my channel and join me in the next tutorial as we work through examples of these Laplace transforms. I thank you so much for watching, and I'll see you in the next one. Bye bye.